Okay, I can put this down. All right. Series. Now, sign up. I am trying to say that we need to have a system. Buildings, it's about scanning. And in it, it's for buildings, small, professional. See, if you area we have here now provide proper structure so that we can fall down. Next one is round shape. Round shape with the dots. And as we have learned from sigma f equals fa, with the ground shape, that must be acceleration. Therefore, so movement of the ground creates force that must be stand. And the beam system that stop not take care of it. That is why we need the parallel system. Okay. Now, so far, I'm a very simple operating system. Okay, try to keep things in the or indeterminate structure. So I, try something like this, perhaps. That's the question. Okay. But indeterminate frame, meaning there are the data react so I think you will first time and no. It's not possible. It's impossible. You have a building that looks like this, right? No floor. Some floor. Let's say if I add one, that something like that. So when you cut the divide, you see the divide comes out. Come out. Those we can solve the reaction, but meaning you know is the reaction by one. But when I cut the diagram, this was one. As you have the right diagram, shear diagram of each element. So that each member will have a process. Okay. Okay. You see, here you have shear axial, and then you have two members. You have shear axial. How many of those we have after we go react? Now we have 6. 6 are known, but you only have 3. So this structure by angle over here, you have what we call indeterminate structure. Now, static indeterminate structure, meaning you cannot use static solve or and in reality, we're going to have more. We're going to have more of this. We're going to have more. So it's urgent and person. was trying to use that you could add areas of like a vocabulary like this is say it's a normal university level. Imperative means urgent and important. It's not only important, it's also urgent. It's imperative. Okay? So it's imperative. We know how to solve the structure that has more than or unknown than so we begin Asha do in different. As you can see, I brought this out just to show that it's normal structures in the real world. Most of them are not. So we can simply say the permanent structures is we have drawn up into indeterminate. Okay. Now, before we go to the frame, let us put this on the B. So we now can get this to the computer. And this session today is about creating your understanding regarding this concept of indeterminate structure. So I am very happy to keep explaining things until it gets into your system. Okay? If you are here listening to me in the class today, you should make the most of it. At least try to make it more than just watching the clip. Because everyone can just go on and watch the clip later on. Try to ask me as many questions as possible. If you don't have questions, you could probably ask me to repeat something that I just said and you didn't get it. Like that too. Okay? So it's about trying to understand what this animal is about. This animal is called statically indeterminate structure. Okay, so let us go back here. Let's say if I have this typical structure. Okay? Now this is determinate, right? So I can say, yeah, it's a determinate structure. It's supposed to be blank. And from that, okay, I will write down a simple cantilever beam with that. Okay, so let's say if this beam has so much deflection at the end, okay, without anything, without any modification, we know that this beam will deflect down like this. Is that correct? This is your typical understanding. So let's call this A and B. So here it becomes say delta B. Okay, the displacement or deflection at B due to your load. So what if I say same beam, but I put the support there? The common understanding is that you know that this support eliminates delta B, correct? It's common sense. If you have a support, the definition of the support from your good old statics would say that, okay, right there, that should not be any movement. So if I put the support at level, with A at B, okay, if I put the support at B in the same level at A, we can simply say that we don't have delta B. This is a very common thing, right? Okay, we don't have delta B because we have the support. So if I replace the support, okay, this is now a typical cantilever beam. Okay, a very typical cantilever beam. Now, let's say with no support, I say there is a force there. this force is unknown. Okay. Now, suppose I don't want to know. I'm trying to find the best way to explain this. Okay. Let's say I want to know this force. I don't know how much it is yet, but I want this force to give me the displacement here. Let's say small delta B. If I set this delta B equal to the capital delta B, now instead of trying to calculate the displacement because you know the force, that's what you've been doing all along, right? Now, instead of giving you the force, or instead of knowing the force, I know the displacement. And I want to calculate the force that gives me the displacement that I know. Can I do that? Maybe I'll write down. Every year that I begin this stuff is different. So you are more than welcome to go back and look at the video clip last year, see what approach that I use. I think it gets different every year, and the nature of the people is that some who learn better by method A, some who learn better by method B. Never know. Just have to try to give them as perspectives or angles as possible if they're okay with one. So let's say before, I'm gonna write this down. I'm gonna write this down this year. Before, force is given. Displacement is obtained. Kind of nice word. Now, displacement is given. Can we obtain force? Can we? I think so, right? Yeah, I think so too. And do you think so, folks at home? Hello? Are you with me? Do you think so? They're not in front of me. They don't have to answer, right? They're probably all fall asleep. So I hope that you think so, okay? Now displacement is given, can be obtained, of course. Okay. So let's say, yes, because we don't have this one. So I'd say yes. Once we obtain the force, that will give us the same displacement. Which means if I combine these two cases together, like this, combine the two. The first case is the cantilever beam with the load that gives you, okay, oops, capital delta B. This is what we call displacement due to actual load. Okay. The second case is force. It's called P. Okay. my life will be better. This is a small delta B. This is displacement caused by P. Okay? If we say they will need more. Huh? Why it keeps getting smaller? Same template. Anyway, right. Hang on a minute. So I'm supposed to well, it's now it's just up. Can I move it? Yeah. Okay. So now let's say if delta B is equal to this small delta B, or you can say delta B plus small delta B equal to 0. What does it give you when the combination of displacement becomes 0? Doesn't that mean the support? Is this the condition of the support? Yeah. So meaning if I redraw this is where you have this condition. Okay? You have the displacement caused by the load, the actual load. And then you have the displacement caused by the load P, knowing that this P will create the same amount of displacement. When you combine them, you would have the condition we call the support, right? Because now the displacement due to the load and the displacement due to this force happen to be equal and opposite. So when you add them up, you have 0 displacement there. And when we have 0 displacement at one place, can we call that place a support? Of course we can. All right. This is something that we call compatibility. Okay? Means that everything has to be compatible. The displacement due to the external load must be equal and opposite due to the displacement caused by P. Now I can let's say I'll try to put this into words, okay? Displacement by load. It's a bit too high. Runs through the reaction. Plus displacement by P, B equal to 0. This is compatibility condition. Now, instead of keep calling displacement by P, I can say this is displacement by the reaction RB. Can I say that? Of course I can. Okay? Meaning, if you are capable of calculating the displacement caused by the actual load, you should be able to use that information to obtain the magnitude of the reaction that will produce that same amount of displacement, but in the opposite direction. But that is the concept. Okay, so instead of writing, are you taking notes here? Maybe I should wait a minute. Take as much time as you need. Try to make notes and absorb the concept. Folks at home, are you okay? Any question? No question. So you see, the difference is that this picture, I should use the capital delta. When you look at this picture itself, it begins from what looks like a determinate structure. And we talk about the displacement here, right? So if you can understand that if it's a typical determinate structure and you have this kind of displacement, we can just find a force to stop this displacement, right? To eliminate this, to make it become zero. If you can find a force to make this become zero, that means that force should be equal to the reaction. So instead of looking at like this, I can say we are looking at this structure. Let me redraw it again. Okay. So let us begin from here. When you see this structure with the look, okay. Now you know there are 4 reactions. Okay. There are 4 reactions. But we start off by talking about the cantilever, meaning I can just I can move useful feature there, right? I can move this out. Remember that this is our real structure. Our real structure has this, but I can remove this out. As a result, when we remove the support, we now have the cantilever beam that we have been introduced at the beginning. So from indeterminate structure, a reaction can be removed So the consequence is, or the consequences are, first of all, we will have deflection. Right? With the support, there you don't have the displacement or deflection. Now I call it deflection. Let's say the displacement, okay? So that keep consistent. Displacement. But keep in mind, when we talk about displacement, if we talk about displacement at that location, we don't talk about displacement anywhere. But it has to be at that location. Because of that, now you have delta B. Now you see, keep in mind that our real structure is this cantilever beam with a roller. Now I just remove the roller out, so I have the displacement, and this structure with one reaction removed. Okay. Yeah. Is called, wait for it, it's called primary structure. Like a prime number. Okay, so that's a consequence. We remove one reaction. We sort of induce the deflection or displacement because the support is no longer there. We just take it out, and therefore you cannot say the displacement at the location where the support used to be will be zero anymore. It will be there. Okay, so now the same structure. I put this back on. I think it's pretty hard to copy the drawing like this, but let me say if I could do it. I'm still persistent. Oh, do it this way. Okay. If I put this back on, okay. Now, without giving the roller back, because you know we can replace the roller by the force this time. So say put this back on. So it's equivalent to having this here, right? Because if you draw a roller, you would, how would we have, we can't. So you can say just put this back on, but just the force. Okay. You know that this force, whatever it is, will have to give you delta B. And now you know, because it is a force from the support, this delta B will have to be equal and opposite to the capital delta B. I'm trying my very best to be literate. Okay. This delta B not very nice.
being the displacement caused by reaction must satisfy compatibility condition or equation, whatever you want to call it. That's condition in short or equation in short, okay? Which is, of course, delta B plus delta B equal to 0. It has to be because it's a support. That's why we say it has to be compatible. Notice that the first delta B, the capital delta, is the displacement caused by the actual load. This delta, capital delta B, is the displacement caused by actual load. But this delta, little delta B, is the displacement caused by the reaction or just one pointer. Can you see? Can you appreciate the differences? This is the actual displacement caused by the load. It's there because we remove the support. This is the displacement caused by the support reaction trying to push this back to 0, or we can say trying to obtain compatibility. Okay. So generally, the first one here, the capital delta B, can be obtained because you know the load, and we have created the determinate structure by removing the reaction. This is what we call primary structure. So you can always obtain this one because we make sure that we remove the reaction so that we have the primary structure that we can calculate displacement. So delta B can always be obtained. And once you know this small delta B is a function of the reaction RB. Meaning you now can solve for RB. Okay. You can see that if I go back to this structure, okay, if I go back to this structure, which is what we are doing here now, I have, let's use this one. If I put delta B out and I put this back on, now you have the structure for reaction, correct? And the number of unknowns exceeds your equilibrium equations by 1. So we call this structure 1 degree of redundancy. R is for redundancy. Okay. Now, redundant is something that you don't need, right? If somebody tells you that, hey, in the group project you are redundant, no, you're not supposed to feel good about it because it means like you know they drag you along, you don't help anyone in the group at all. So in this sense, a redundant is the reaction that we don't actually need. Your system can survive without it. but yet we want redundant because, first of all, your structure will become stronger. But this structure, for example, you look at this. This structure is much stronger than just a typical cantilever beam. Because you see, there is another support to help reduce the displacement at the end. So the structure is stronger. When the structure becomes stronger, it means that your internal force will be less. And therefore, when the internal forces become less, your member will be smaller. And the fact that you have the redundant, something beyond your need, means that it will give you extra safety. Because if you have a determinate structure and something goes bad, your structure is so ready to collapse. With extra redundant, you will have some reserve somewhere. Okay, so in the real world, we usually prefer the indeterminate structure, not the determinate one. Nobody builds the determinate structure. You will not just go out there and work and see, high-rise buildings, completely consist of determinate structures. Impossible, because it would mean that you would build a truss, right? The truss to withstand the wind load and the earthquake. It's untenable. So this is real, and this is your first foray. Again, trying to use crazy vocabulary, but foray is a word. Right? This is your first journey, okay, into the real world. So if you are in the matrix, would you take the red pill or the blue pill? Anyway, you can't choose to take any pills because this is part of your curriculum. Okay, you have to go through it. So yeah, here, this is a redundant. So now we are repeating the same process again. Now I can say we remove this. We remove the redundant. Instead of saying your reaction is remove, one reaction is remove. Typically, people would say we remove redundant. And now keep in mind, be mindful of the word. We can remove it because it's a redundant. If it's not, you cannot remove it. Okay. Let's say you have a simple beam, remove the reaction because you don't have the redundant. But now you have the indeterminate structure. You have the redundant, unnecessary reactions. You can remove them on one condition. That is, remove and here your structure must remain safe. Okay. And we remove it so that we have the primary structure, the one that you can take care of. Okay. Once you remove this, it means that you can have the displacement that should be equal and opposite to the displacement produced by the reaction itself. And that condition is called compatibility. Okay. So now, is there any question? Go quiet again. So now, let's say we have 5 minutes left. I don't really want to start a new problem, but because it's been so quiet, so I don't have a choice. Okay, let's look at it. It's a simple beam, and we are trying to take a look at midspan. Okay. Again, if it's a simple beam, and we focus at midspan, you do we have the delta B at midspan? Okay, but if again you don't really see super beam anywhere, let's say instead of having a simple beam, now you have a beam with another support. Now this looks more typical because it's what we call a continuous beam. It's beam with more than one span constructed continuously. So, meaning if I hold this B again, this RB is there to eliminate delta B. That's support, right? If you have the support here, you will not have delta B. So in the same fashion, this RB should give you delta B that is equal to capital delta B. Keep in mind, because I think some of you are not really mindful, when I write the first condition here is the condition with the actual external load. This is the condition with the reaction. Okay, so be mindful of what condition you are going to calculate the displacement, because there have been some students who mix them up, and it's been there are quite a few of that every year, and I bet there's going to be a few of that this year as well, especially those who are not in the class. So again, if we have the real condition that looks like this, it comes from these two. Okay, this and that. And, I suppose I should go back on. Okay. Right, and again, the compatibility equation would be delta B plus delta B equal to 0. Okay, and this is your primary structure. Okay, so you've come this far. I believe the first thing that you need to be able to do is to calculate displacement. No two ways about it. And you've done it before. And as far as I know, you've done so many methods with them. For example, Compatibility Equation, moment of the moment area. I'm always confused that. They call the moment area method, right? But actually it's the moment of the moment area. You can recall that? And I believe if you have come from a Untitled Chapter, you have learned the virtual world as well, right? Am I right? Am I right? Have you? The virtual world? If
Yes.
nobody says anything to me, I will assume that you've learned it before, and I'm not gonna, spend a lot of time doing it. How about that? One thing about the virtual work is that it's been there for more than 300 years. 300 years. I'm not kidding. Now, that means they could do it without calculator, computer, air condition, elevator, escalator, cars, TVs, mobile phones, or etc., etc., etc. And you have all kinds of technology in the world supposed to be able to do it. Right? The virtual world by the great Bernoulli. The Bernoulli family, the family that has given you all help. The Bernoulli equation, the virtual work, and many more. It's the entire family. There wasn't one Bernoulli, there's just many of them. Okay, I think that's 10:20. So I'm just gonna stop the record and take a break. 10-minute break.